if it's going to decrease, increase, or it's going to remain unchanged, or obviously not enough information. So to handle these type of questions, this chart is perfect, right? Because if you think about it, let's say if I keep, these are my variables, so if I'm changing temperature and I'm changing volume, I get to see what's going to happen to my entropy. Right? So in this case, a few moles of nitrogen gas, that's the system. The nitrogen gas is heated from 8 degrees centigrade to 28 degrees centigrade, and also expands from a volume of 2 liters to 10 liters. So in this case, we are increasing the temperature, right? And we're also expanding the volume. So that means our entropy is also going to be increasing. Make sense so far? Okay. Right, so you're basically saying, okay, this is my system, and this is what we're going to do to the system, and this chart basically helps us get the answer. So same thing here. We're going to say the helium expands from a volume of 2 liters to 15 liters, while the temperature is held constant. So we know temperature is constant and volume expands, so that will be, our entropy will then also increase. The acetone is heated from negative 14 centigrade, right? So all we know here is temperature, right? So in this case, since we know the temperature, we don't know what's happening to the volume, so we can assume that the volume is going to stay consistent. So let's say temperature is going up, volume staying consistent, so that means our entropy is going to increase. Any problems with this type of question? Pretty straightforward. Use the chart, and it's really easy. Okay, perfect. All right. Okay. Okay, so next one is predicting qualitatively how entropy changes with mixing and separation. So again, we have our system and what we're going to do to the system, and we want to figure out what's happening to delta S. So a solution made of potassium bromide is in water and at 26 degrees centigrade. 50 milliliters of pure water is added to the solution. So how do we answer these type of problems? Okay, so So one of the key things is when mixing, right? If you think something's mixing, our entropy is going to increase, but also my temperature and the volume has to stay the same. And delta S also equals when there's no change to the initial system, right? Makes sense. So let's go here, right? So in this case, what we're doing is we have a solution of KBr, and we're just adding more water to it. So what's going to happen to the KBr? You're just basically increasing the solubility so that you're mixing the solution, right? So now more KBr is going to be able to turn into ions, like we talked about before. So you're going to have a K plus and a Br minus in the solution by adding this pure water. And so in this term, it's going to be called mixing. And since it's mixing, our delta S is increasing. So, and when it says total volume, technically it means the volume of your, let's say if you're going to add more KBr to it. That's what they're referring to as staying the same. All right. Next one, 300 milliliters of sodium, solution made from potassium bromide dissolved in water. 0.5 grams of potassium bromide crystallized out of the solution without changing the temperature. So what's happening here is we're not doing a mixing. We're not creating more ions of KBr, but what's happening is the KBr is coming out of the solution. So remember when we talked about solubility, now the solubility is going lower. So now we have solid in our solution, which is the 0.5 grams of KBr. So since we have something coming out of the solution, or we have the solubility decreasing, it's also going to decrease the entropy, or the delta S is going to go lower. Right? So then the next one, a mixture of krypton gas and argon gas at 5 atm and 15 degrees centigrade. An additional 2 liters of pure argon gas is added to the mixture with the pressure kept constant at 5 atm. So in this case, what's happening is, since you've added more argon, what's happening to the initial reaction is now the argon is going to mix in, obviously, since we have some more argon gas and krypton gas, these two are going to mix with each other. Right? Since they're the same, they're going to mix with each other, and since we're keeping the pressure constant, so it's not going to change the total volume of the container, right? We're just keeping the pressure consistent. This is then going to then increase our entropy. Make sense? Okay, let's see. All right. Predicting reaction entropy. So first thing I would do is look at these 3 rules for these type of equations. Delta S increases, delta S increases when a solid or a liquid turn into a gas. Right? So if you go from your reactants are a solid and a liquid, and then on your product side you have a gas, then you know your entropy is increasing. Obviously, vice versa, if you go from a gas to a solid, then your entropy is going to be decreasing, right? So this is showing from the increasing side, but if you reverse it, it'll be the decreasing side. So delta S also increases when you mix pure substances, and when you have more moles of gas. And obviously this into, for some reason, should be here. Right? Okay. When you have more moles of gas on the product side than on the reactant side. That's also showing that you're going to increase your entropy. Obviously, if you have more moles on your reactant than product, then you're decreasing, right? So let's look at the question. So we have this reactant making this product, and we want to figure out what's happening. Well, look at our rules and see if any of them match up with this. Well, we see solid and liquids, and the product is a solid and a gas. I apologize for that. So automatically, that's our first rule. So we already know what we're going to do and how to answer this one. In this case, since we're going from a solid and a liquid to a gas, we already know our entropy is increasing. All right. Now we look here. Everything is gas, so that's not rule 1. We're not mixing pure substances, so that's not going to be 2. But in terms of 3, let's check the moles out. So we have 1 mole of N2, 3 moles of H2, and then on the product side we have 2 moles of NH3. So that's similar to this, right? When you have more moles on the product side than the reactant, but it's just the reverse of it. So since this is the reverse of the third rule, we know we're going to have a decrease in our entropy. And in this, you have silver chloride, and this is a solid, and then you're going into ion form, so you know you're adding water to this solution. So what's happening is you're then also creating more moles, right? Because there's 1 mole of silver chloride, and then altogether 2 moles, 1 mole of silver, 1 mole of chloride. So in this case, you're going to have an increase in entropy. So far, so good. Just basically learn the 3 rules and then apply it to these. But any questions on this? Let's see. Oh, give me 1 second. Let me fix this. Okay. So next one is using the second law to predict spontaneous change. Not too bad. Obviously, you see the same rules that we had before. And this chart will kind of help you understand what's going to happen spontaneously. So let's break it down. All right, so we already know, first question, it says, during an endothermic chemical reaction, 4 moles of gaseous reactant are turned into 2 moles of gaseous product, right? Automatically, what we know is we can solve for delta S, right? These rules are going to be solely for delta S, what we kind of did before. So in terms of this, since we're going from 4 moles on the reactant and then 2 moles on our product, we're going from bigger moles to smaller moles, which means negative delta S, right? So delta S is negative. Now the next thing we need to know is what's happening to the surroundings, right? Because the system technically is delta negative, right? The surrounding, what's happening to the surrounding. So we're saying during an endothermic chemical reaction. And we know endothermic means you're absorbing energy. But there has to be a place where you're taking that energy from. So you're taking it from the surroundings, right? You're taking energy from the surroundings into the system. Make sense? So it makes sense why the surroundings are going to be negative, because they're giving energy to the system. Okay. Right? So once you see endothermic, you know surroundings are going to be negative. Obviously, if you saw exothermic, that means surroundings are going to be positive, right? Because the system is giving off energy to the surroundings. But in this case, the surroundings are giving off energy to the system. And so that's negative, and we know the system is negative because it has less moles. We don't need to know about the universe, just really need to focus on these 2 parts. And so now that I know that, so I have negative and negative, then the only thing that I can get is this one, so we know it's not going to be a spontaneous reaction, right? Next one, a solid absorbs heat and turns into a gas, right? Perfect. Well, absorbing heat means you're taking energy from somewhere else. So you're taking energy from the surroundings. So automatically, I know my surroundings is going to be negative, right? Delta S surroundings. Now I got to figure out what's happening to the system. Well, it turns into a gas. So I look at my three rules, and I see when a liquid or a solid turns into a gas, right? A solid turning into a gas. Perfect. So my delta S is going to be positive. And so I look for something that's like that. The only thing that's like that is this one. So we can't decide if it's spontaneous or not. So far, so good? Okay. Next one, a solid precipitates from a solution, absorbing heat as it does so. Perfect example. We already know since it's absorbing heat, delta S is negative. I'm sorry, delta S surroundings is negative. And since the solid, well, all right, put it this way. Since the solution is now having solid come out of it, it's the same question that we did before, right? And what that means is you're decreasing the system, right? Opposite of mixing is right coming out of the solution. So that's also going to be negative. So we have two negatives, so then this answer is going to be no. Any questions on this? Okay, pretty straightforward. All right, so let's go into some calculation. Like, and if you notice, these chapters after 14, pretty relatively easy compared, right? It's still a little difficult because you have to understand what's going on, but easier compared to 14 and 13 because they have so many calculations. Where the calculations are smaller, shorter, and quicker to get through. Yeah. So, calculating reaction entropy using standard molar entropies of reactants. Whole bunch of nothing, just saying summation of products minus summation of reactants. So you kind of, I don't know if you guys remember doing this in Chem 103, similar things, right? When we were doing it for delta H. But in this case, we're doing it for delta S. You can also do the same thing for delta G. Obviously, I'll show you that in a second, but yeah. So all you're basically doing is saying, I'm going to go into Alex, I'm going to look at the values. Sorry. All right. So, right, go into Alex, look at the values for the delta S, which are shown here. And then all you do is say, my product side minus my reactant side, right? So these are my products. Make sure the coefficient that's from the equation is in front, right? So if I have two irons, I need to put 2 times that delta S. And if I have 1 aluminum oxide, I need to put 1 in front of that delta S, right? And then I make sure I add these up together, minus whatever's added up for the reactants, and then I get my total on my delta S for this reaction, which is going to be negative 39 joules Kelvin per Kelvin. Any questions about this? I mean, the hardest part is just making sure that you find the correct values, and then you just add and subtract. Yeah, so much easier. Right. Okay. So this is another question that you guys hopefully did in 103. So it should look familiar. So standard reaction free energy delta G is negative 835.5 kilojoules for this reaction, right? Use the information to complete the table below. Round each of your statement to the nearest kilojoule, right? Now all you're doing here is just saying this and this, what's the difference? Right? So I see here, what's the difference between this reaction and this reaction? Well, they're flipped, right? This is now on the reactant side, and this is now on the product side. So since it's flipped, all you do is multiply it by -1, right? Or you change the sign. Instead of being positive, it'll be negative. Make sense? Okay. Next part, saying, okay, what's here? What's happening here? Well, I see it's still flipped, but there's another change to it. The other change is it's multiplied by 3. Right? That's how we get 3 in front of this aluminum, 6 in front of this iron, 6 in front of this aluminum, and 3 in front of this. So since I have that, what I'm going to do is basically I can change the sign and multiply by 3, or I can just times it by -3. Okay, right? So it makes sense where I got the -3 from, right? Because I know it's flipped, so I'm going to change the sign. So the negative is going to change that. And since everything is multiplied by 3, that's where I get the 3 from. And that's how I get this answer. And in this case, it's not flipped, so I don't have to use a negative. But what's the difference? Well, it's multiplied by 2. So I just multiply by 2, and then I get the answer. And that's it. Any questions on this? Right? Easy. So you can already tell that your next exam, especially that's going to be dealing with all this stuff, so much easier than the one that you did before. Unless, well, yeah, let me not say that. But yeah. All right. Calculating delta G from delta H and delta S. So, in terms of this, obviously there's formulas. Did I write that? Yes, I did write that. Okay. So, if you want to read this, you can. I'm just getting right into solving it. So, in this case, they give you your delta H, they give you your delta S. You have to find your delta G, and you have to figure out if it's going to be spontaneous. So you have to figure out, well, how am I going to do that? Right? So I see this equation, I'm saying, what am I going to do first? Well, this chart will tell you if it's going to be spontaneous or not. So it's all dependent on delta G. Right? So if delta G is less than 0, then the reaction is spontaneous. If delta G is greater than 0, then the reverse is spontaneous. And if it's equal to 0, then it's not spontaneous. Right? So that means this question is going to be answered once I answer this one. So now I have to figure out, well, how do I get delta G? Easy enough. So you're going to use this formula, right? Delta G equals delta H minus T. This is going to be temperature, and delta S. All right. And if obviously if you want to solve for, you just have to manipulate the formula. So one thing, yes, I was going to mention that. One thing you have to notice is the temperature, so the 22 degrees Celsius, has to be in Kelvin, right? To be able to find, because then you're going to be able to cancel out the delta S. So you see the unit for delta S is Kelvin, but also you have to make sure the unit for both of these are the same. So in this case, if you need kilojoules, you're going to have to then also formulate this into kilojoules before you start solving. Does that make sense? right?